Hello, and welcome back, everyone. In this video, we will be diving into one of the more sophisticated image classification architectures known as the Inception-ResNet architecture. We will explore what it is, its design architecture, some of the ideas proposed by the team, and how it compares to the Inception architecture. So let's get started. Inception-ResNet architecture was developed by researchers at Google in 2016. As the name suggests, this architecture combined the best elements from both the Inception and the ResNet architectures. More concretely, the filter concatenation stage of the Inception architecture was replaced with residual connections. The team at Google proposed that this approach of combining the best elements from both would help Inception get all the benefits of the residual approach, while still retaining its computational efficiency. This slide shows the core design of the Inception-ResNet module. It incorporates the Inception module, which allow the network to choose from various scales of convolutional operations. This is coupled with residual connections, which help in overcoming the degradation problem by allowing activations to flow through the network without severe reduction and modification. A scaling factor is also present, and is combined with the residuals before their addition with the activations of the previous layer. Using a large number of filters make the residual variance unstable and the network to stop learning. The scaling of the residuals is done to solve this problem. These features solve different challenges. The Inception modules handle the choice of scale effectively, while residual connections streamline the training process even with deep networks. The scaling parameter, whose values range between 0.1 and 0.3, helps control the magnitude of outputs, ensuring stability. Let's now look at the overall design. The Inception-ResNet architecture starts with a STEM module, which is just a combination of convolution layers with a pooling layer in between. Next comes the stack of Inception-ResNet A modules. This module, as well as the B and C modules, are modified versions of the Inception-ResNet module we just saw, with the difference being the number of convolution layers and the size of the filters. I would suggest not to worry about the actual design which the team came up with through lots of permutation and combinations to keep the architecture stable. Instead, focus on the general concept and the bigger idea. Coming back, each of the Inception-ResNet modules A, B, and C are followed by their own respective reduction modules. As the name suggests, these were added to streamline the dimensionality of the depth, as well as reduce the grid size to ease computation downstream. At the end, a pooling, a dropout, and a dense layer were added to condense the knowledge and generate a classification. Coming to some core ideas discussed in the paper, one important one was the confirmation by the team that residual networks increase the speed of training significantly for Inception-ResNet networks as compared to similar non-residual Inception networks. Another thing that the team pointed out was that similar to the ResNet team, they too used projection shortcuts, or a one-by-one convolution layer, without activation to scale the dimensionality of the residual portion before the residual addition. Finally, the team noted through experimentation that using more than 1,000 filters made the residual variance unstable and the network to stop learning. The team solved this problem by scaling the residuals, or the Inception side, by a factor between 0.1 and 0.3 before addition, as we discussed when we looked at the Inception-ResNet module. The Inception-ResNet architecture offers several advantages, like reduced training time because of its efficient use of inception and residual pathways, and versatility in handling different image scales. However, it comes with its own set of complexities that might increase the computational resources needed. When compared to its predecessors, the original Inception network primarily focused on multi-scale processing, but lacked the shorter paths for gradients during backpropagation. The Inception-ResNet architecture addressed this by using residual connections from the ResNet design to promote easier learning with fewer epochs. This amalgamation not only preserved model depth and neural pathway diversity necessary for detailed feature extraction, but also ensured that the model remained computationally efficient, which is critical for many real-world AI applications. Later experiments have demonstrated that Inception-ResNet performs robustly and achieves higher accuracy without significantly increasing computational burden. To sum up, the Inception-ResNet architecture stands out by delivering learning flexibility, high accuracy, and computational efficiency, a perfect three-in-one combo, making it an excellent choice for AI applications requiring superior image classification performance. And that is all for this video. In the next video, we will explore this architecture for ourselves using Python and TensorFlow. So, see you there.